Hello everyone, I am Jayabrata Chowdhury, a PhD student at Robert Bosch Center for Cyber Physical Systems, Indian Institute of Science, Bangalore. This talk is about our paper Graph-Based Prediction and Planning Policy Network (GP3Net) for scalable self-driving in dynamic environments using deep reinforcement learning with my co-authors V. Shivaraman, Professor Suresh Sundaram, and Professor P.B. Sujit. I am thankful to Qualcomm for supporting this work with the Qualcomm Innovation Fellowship.
Imagine a bustling city intersection. Car, bikes, pedestrians all weaving their paths. For an autonomous vehicle or AV, it is not just a problematic scene, but a puzzle to solve. The challenge is navigating safely in this non-stationary environment. But how can an AV maneuver through a non-stationary world without a clue? The answer lies in understanding the driving context, like it's reading the mind of fellow road users and deciphering their intentions. By analyzing movement patterns and environmental cues, we can infer what others are likely to do. Are they turning, yielding, stopping? This insight becomes the AV's secret weapon, the key to predicting traffic flow. Armed with this knowledge, the AV can plan its own moves. It avoids collision, respects traffic rule, and navigates smoothly. It is not just about reacting to the present, but anticipating the future. Recently, works have been done on rule-based motion planning algorithm. Rule-based methods perform well for known scenarios where the rule has been developed. However, rule-based systems can need help to generalize in new driving scenarios. Imitation learning from some expert driver behavior is an excellent alternative design idea for motion planning for AV. The deep imitative model showed a good performance. However, it is well known that imitation learning can suffer from distribution shift problems. To mitigate this issue, researchers recently started utilizing reinforcement learning for motion planning. However, these works need more detailed interaction modeling with other traffic participants. A recent work in autonomous driving utilizes a graph attention network to model the intricate interactions between multiple road users. Trained to mimic expert drivers, it has demonstrated good performance on various benchmark scenarios. However, there is a crucial catch. Expert driving data typically lacks near collision situations. When faced with such an unexpected event, DigNet, relying solely on learned imitation, may struggle to choose the safest maneuver. Here's where our work takes in the world. We propose a predictive planning algorithm powered by deep reinforcement learning for safe motion planning in autonomous vehicles. First, our algorithm predicts the future behavior of other traffic participants, enabling the ego vehicle to proactively plan even in unexpected near collision situations. Second, our approach goes beyond simply imitating expert behavior. It empowers the vehicle to learn and adapt to diverse driving scenarios, leading to more robust and resilient performance. For predictive planning algorithm, at first a prediction model has to be used. For this, we built a dynamic spatiotemporal graph where each traffic participant is a node connected by edges representing their interactions. Now we need to understand their movements. We use LSTM networks to analyze each node's position, velocity, and acceleration, capturing how they move over time. However, it is not just about their trajectories. Hence, another LSTM network, the edge encoder, analyzes the connections between nodes, understanding how their movements influence each other. This information is then condensed into a latent space. We use a conditional variational autoencoder to sample the latent space to generate possible future trajectories for each participant. The output of the decoder of CVA is parameters for Gaussian mixture models. Gaussian mixture models provide multimodal prediction for trajectories. Now, there can be some uncertainty in the prediction. Hence, there should be some way to incorporate prediction uncertainty, and the planning module should be aware of this prediction uncertainty. We chose the most likely future position from the Gaussian mixture model. Also, we know about the root mean square error for trajectory prediction from the prediction model training time. Hence, we create a 2D Gaussian patch centered on the position with its size reflecting to the predicted uncertainty with root mean square error. The bird's eye view of the future with each participant's position with encoded uncertainty becomes the AV's roadmap. It allows the AV to navigate safely, anticipating the most likely paths and the potential surprises the road might hold. The predicted bird's eye view marks show where other vehicles and pedestrians are likely to be in the near future. Combined with information about the road layout with lanes, stop signs, past movement patterns, and AV's odometry measurements, this bird's eye view marks forms the input for the driving model. This information is then fed to a combination of convolutional neural networks and fully connected layers. These layers shift the data, extracting hidden patterns and insights. The processed output is passed to the final fully connected layers to produce beta distributions over steering and throttle values. A sample is then taken from the beta distribution to control the AV. The AV learns by doing, experimenting, and adjusting its decisions based on rewards. We use a dense reward to encourage good behaviors, points for smooth driving, following the route, and avoiding collisions. This feedback loop helps the AV learn quickly and efficiently. We use a modified proximal policy optimization or PPO algorithm with an entropy term for safe exploration. This encourages the AV to try different options while keeping things safe. During the training phase of our reinforcement learning model, we conducted a qualitative analysis to assess the efficacy of the graph-based prediction model. We tracked and plotted several metrics, including the reward obtained, traffic participant collisions, layout collisions, and total score. These metrics were compared for two distinct scenarios. One incorporated trajectory prediction and another excluding it. As we visualized the simulation during training, we noticed an interesting pattern. Up until 5 million steps, our vehicle was primarily focused on mastering route following in various scenarios while avoiding collisions. However, after 5 million steps marks, the car faced a more significant challenge, preventing accidents in high adversity situations. At this point, the RL model, equipped with enhanced trajectory prediction, demonstrated its superiority. It overcame this performance barrier more effectively than the model without the trajectory prediction module. This emergent behavior is evident in the first two plots related to the reward obtained and vehicular collisions. The trajectory prediction module gave our vehicle an accurate implicit model of the environment dynamics and inherent uncertainty. This framework expedited the agent's ability to achieve higher rewards and commit fewer infractions as the training progressed. Compared GP3Net with different works on Carla leaderboard benchmarking scenario towns. Some works use graph convolutional networks or GCNs to encode the interaction between traffic participants. Another model uses a graph attention network or GAT for encoding. Recently, DigNet modified the GAT architecture for added context awareness. We compared GPT-NET's performance with two metrics. One metric is success rate, which measures how often the AV reaches the destination without collisions. Another metric is driving score, which considers route completion, collisions, and traffic rule violations. The comparative analysis shows that GPT-NET outperforms previous models in success rate and driving score in all towns. A significant improvement can be seen in Town 5 with urban environment, Town 6 with highway driving scenarios, and Town 4 with mixed traffic. These diverse environments demanding speed and adaptability are where GPT-NET truly shines. On average, it outperformed all others by 3.8% in success rate and 8% in driving score, with a remarkable consistency of only 1.5% for the standard deviation. We also compared the performance of GPT-NET with the hierarchical interpretable imitation learning framework for the performance on Town 1 and Town 2 different weathers. And here also GP3Net consistently performed better in all weather conditions.
We performed ablation studies of the GP3Net framework on the Carla no-crash benchmark, recording several safety-critical parameters to evaluate the compliance of the framework to traffic rules and safety. The no-crash benchmark takes place on Town 1 and Town 2 maps with trained weather and new weather conditions. Our vehicle can thoroughly follow the designated route in Town 1 and Town 2, getting over 95% end reach on average. The success rate is great. We can observe that the vehicle does not violate traffic lights. It can be noticed that the vehicle and walker crash rates are low and do not change much. In summary, GP3Net proposes a solution to domain shifts and handling unexpected scenarios. The spatiotemporal graph captures the dynamic interactions between traffic participants. The prediction model infers future behaviors and uncertainties of other traffic participants and provides AV with an informed decision capability for navigating uncertain non-stationary environments. Future works can incorporate the dynamics models for better modeling interactions in real-world scenarios. I thank you all for listening and hope to meet you at the AAAI conference.